This video is for Chemistry in the Earth System, Unit 2.1, Parts of the Atom. Today's essential question is, how does the structure of the atom determine both the identity of matter and the energy that it can release? Hello, baby birds! Today, we are going to explore how something as tiny as an atom can hold enough energy to power massive ships through solid ice. This topic is called Parts of the Atom, and by the end, you'll understand not only what makes up an atom, but also how the structure of those parts connects directly to energy, matter, and the technologies that run our world. Just check out this icebreaker ship. Speaking of icebreaker ships, imagine the Arctic Ocean. Thousands of kilometers of frozen sea, with ice thicker than a car is tall. Traditional ships that burn coal or oil couldn't carry enough fuel to cross it. Once they ran out, they were stranded in the ice. In 1959, engineers solved that problem by tapping into a new kind of power, the energy inside atoms. They built the Lenin, the world's first nuclear-powered icebreaker. Instead of hauling tons of fuel, it carried a small uranium reactor. You see, when uranium atoms split, which is a process called fission, each atom released incredible heat, millions of times more heat or energy per atom than burning fuel. That heat produced steam. The steam turned turbines, and the turbines drove the ship through ice that no other vessel could touch. Think about it. Energy stored in the tiniest building block of matter was strong enough to push a 16,000-ton ship through 3 meters of solid ice. Every atom, no matter what element it belongs to, is built from just 3 types of subatomic particles. First, in the very center, or nucleus, are the protons. Each proton carries a positive charge and has a mass of about 1 atomic mass unit, or AMU. Right beside them are the neutrons, which also have about 1 AMU of mass, but no charge. They're neutral. Together, protons and neutrons make up almost all of the atom's mass. Orbiting far around the dense nucleus are the electrons. Each electron has a negative charge and an incredibly small mass, which is only about 1/1800th of a proton's. Even though electrons weigh almost nothing, they fill most of the atom's space in what we call the electron cloud. So keep this in mind. Protons are positive, electrons are negative, neutrons are neutral. Their arrangement and balance are what determine whether an atom is stable, charged, or part of a specific element. Now let's zoom in for a closer look at how these particles fit together. At the center of every atom is the nucleus, made of tightly packed protons and neutrons. Almost all the atom's mass, nearly 99.9%, is concentrated right there in the nucleus. If the atom were the size of a football stadium, the nucleus would be smaller than a marble sitting at the 50-yard line. Surrounding that nucleus is the electron cloud, a region where electrons move extremely fast. This cloud makes up almost all the atom's volume, even though electrons themselves are incredibly light. So, atoms are mostly empty space. But that space defines their size and how they interact with other atoms. When the number of protons equals the number of electrons, their positive and negative charges cancel, meaning the atom is neutral. If that balance changes, meaning if electrons are either gained or lost, the atom becomes an ion, carrying a charge. But remember, only protons and neutrons live in the nucleus. Electrons orbit outside. That distinction is key to understanding how atoms bond and form everything around us. So, if every atom is made of the same 3 particles, protons, neutrons, and electrons, what makes one element different from another? The answer is the number of protons that are in the nucleus. That one number, called the atomic number, completely defines the element. For example, hydrogen always has 1 proton, never more, never less. Helium always has 2 protons. Carbon has 6, and gold has 79. If you change that number of protons, and you no longer have that same element at all. You've created something entirely new. That's why the periodic table is organized by atomic number. Each step across the table represents one more proton in the nucleus and one more electron in the surrounding cloud. Those patterns determine an element's properties, its reactivities, the compounds it forms, even its color and phase at room temperature. So, the atomic number isn't just a label, it's an identity code for every atom in the universe. Now that we know that an element's identity comes from its number of protons, let's look at what happens when the number stays the same, but the neutrons change. These variations are called isotopes, atoms of the same element that have the same number of protons but different numbers of neutrons. Because protons stay constant, the atomic number never changes, but the mass number does. Take carbon, for example. Carbon-12 has 6 protons and 6 neutrons. Carbon-13 still has 6 protons, but now 7 neutrons. And carbon-14 has 6 protons and 8 neutrons. They're all carbon, but each has a slightly different mass. So here's the key idea. Not all isotopes are radioactive. Most elements have stable isotopes that never change over time. Only certain combinations of protons and neutrons are unstable. Those are the ones that eventually release radiation as they seek stability. Understanding isotopes helps scientists identify elements in space, date ancient fossils, and even power reactors. Same element, same identity, but a different nuclear makeup, and sometimes very different behavior. Hydrogen gives us the simplest and clearest example of how isotopes work. Every hydrogen atom has 1 proton, but that's what makes it hydrogen. But the number of neutrons can vary. The most common isotope is hydrogen-1, also called protium. It has 1 proton and no neutrons, and makes up more than 99.9% of all the hydrogen found in nature. The next isotope is hydrogen-2, or deuterium. It has still 1 proton, but now 1 neutron, giving it roughly double the mass of protium. Because it's heavier, it's sometimes called heavy hydrogen and is used in nuclear reactors and scientific research. The rarest form of hydrogen is hydrogen-3, or tritium. It has 1 proton, but 2 neutrons, making it unstable and radioactive. Tritium is used in specialized applications such as fusion research and certain emergency lighting systems. Notice that all 3 isotopes have the same number of protons, so they're all hydrogen. But their different neutron counts change their mass and sometimes their stability. This idea, same element, different neutrons, is fundamental to understanding nuclear energy. Now that we've seen how isotopes differ, let's clarify 2 numbers you'll see on almost every periodic table entry: the atomic number and the mass number. The atomic number, written as Z, tells us the number of protons in an atom's nucleus. It's like the atom's fingerprint, meaning no 2 elements share the same one. Hydrogen's atomic number is 1, helium is 2, carbon's is 6, and so on. That number also tells us how many electrons a neutral atom has. The mass number, which is written as A, represents the total number of protons plus neutrons. Because neutrons add mass but no charge, A changes from isotope to isotope. It's always a whole number. Since you can't have a fraction of a proton or a neutron, it's always a whole number. So, when you see a symbol like carbon-12, that means 6 protons and 6 neutrons. Carbon-14 means 6 protons and 8 neutrons. Both are carbon, meaning they have the same Z, but they have different A. In short, Z equals the identity, and A equals the mass. Understanding both lets us describe isotopes perfectly and describe and calculate the neutron counts with ease. So let's apply atomic number and mass number to a real example. Gold has an atomic number of 79, meaning every gold atom has 79 protons. The isotope gold-197 has a mass number of 197. So to find the number of neutrons, we subtract 197 subtract 79, which is equal to 118, meaning 118 neutrons. This process works for any element. Carbon-14 is 14 minus 6, which is equal to 8 neutrons. Oxygen-16 is 16 minus 8, which is equal to 8 neutrons. It's a quick way to identify isotopes and understand their stability. Now let's look at isotope notation, the standard way to write this information. The mass number goes as a superscript, the atomic number as a subscript, and the element symbol to the right. So gold 197 is written as seen on your screen here, 197 over 79 with AU to the right. Carbon-12 will be written as 12 over 6 with a C to the right, and carbon-14 would be written as 14 over 6 with a C to the right. This shorthand tells us the element, the isotope, and important clues about stability, all in a single symbol. When you look at the periodic table, even the periodic table that you've taped to the inside of the back cover of your interactive notebook, you'll notice that the atomic mass listed under each element isn't a whole number. For example, carbon's mass is about 12.011, meaning not exactly 12. But that's because most elements exist as a mixture of isotopes in nature, and the atomic mass you see is actually a weighted average of all those isotopes. Think of it like finding the average grade in a class. If one test counts more than another, it affects the final score more strongly. The same idea applies here. Isotopes that occur more often in nature contribute more to the average mass. So, an element with one very common isotope and one rare isotope will have an atomic mass closer to that of the common isotope's mass. That's why these numbers usually include decimals, because they reflect real, natural variation. This is how scientists can link what we see on the periodic table to what actually exists in nature. Here, let's walk through the step-by-step method for finding an element's average atomic mass using its isotopes. So step 1, we will start by collecting the data, meaning the percent abundance and the atomic mass of each isotope. In step 2, we multiply each isotope's mass by its abundance, but the percentage must be converted into a decimal first. Step 3, we add all of those products together. The total you get is the element's average atomic mass, which is the value shown on the periodic table. This method works because it reflects how often each isotope appears in nature, giving us a true weighted average. So let's put this concept into practice by calculating the average atomic mass for magnesium. Magnesium has 3 naturally occurring isotopes: magnesium-24, magnesium-25, and magnesium-26. Step 1, convert each percentage to a decimal. So 79% becomes 0.79, 10% becomes 0.10, and 11% becomes 0.11. Step 2, multiply each isotope's mass by its decimal abundance. Step 3, add them all up. 18.95 plus 2.5 plus 2.86 is equal to 24.31 AMU. Step 4, compare your result to the periodic table value. It lists magnesium's atomic mass as 24.305 AMU, which confirms our calculation. Now that we can calculate isotope masses and identify atomic numbers, let's summarize what each particle actually tells us about the atom. First, the protons, meaning the number of protons, determines the element's identity. 6 protons means carbon, 8 means oxygen, 79 means gold. If you change that number, you change the element itself. Next up, neutrons. The number of neutrons identifies which isotope of the element you're dealing with. Carbon-12, carbon-13, or carbon-14 all have the same number of protons, but different numbers of neutrons. That difference affects their stability and mass. Then, the electrons. Comparing the number of protons and electrons tells us the atom's charge. If they're equal, The atom is neutral. If electrons are lost or gained, it becomes an ion. Finally, when we add protons and neutrons together, we get the mass number, which describes the atom's overall mass. By combining these three pieces of information, identity, isotope, and charge, we can describe any atom in the universe with complete accuracy. So let's return to the big question that started this lesson. How can something as small as an atom power a ship through solid ice? The answer lies in the binding energy inside the nucleus, the tremendous force that holds protons and neutrons together. This energy is released when certain atoms undergo nuclear reactions, either by splitting apart, which we call fission, or combining together, which we call fusion. In nuclear fission, a heavy atom, such as uranium, breaks into smaller atoms, releasing both particles and heat. That heat boils water, produces steam, and spins turbines, exactly how the Lenin was powered. In fusion, light atoms like hydrogen combine to form heavier ones, releasing even more energy. And this is the same process that fuels our sun. But not all atoms do this. Only those with unstable nuclei, meaning certain isotopes, release energy naturally. Stable atoms keep their binding energy locked away. The science of atomic structure doesn't just stay inside the classroom. It has life-saving applications in the real world. One powerful example is the medical use of iodine-131, radioactive isotope, which is a radioactive isotope of iodine. The human thyroid gland naturally absorbs iodine to make hormones that regulate metabolism. Doctors take advantage of that fact by using iodine-131 to diagnose and treat thyroid disorders, including certain types of cancer. When a patient takes a small, controlled dose of this isotope, the thyroid absorbs it just like normal iodine. Then as iodine-131 decays, it releases beta radiation, which selectively destroys diseased thyroid tissue without damaging the rest of the body. It's a precise, targeted therapy that is made possible by understanding isotopes and their nuclear decay. So let's pause for a quick check for understanding before we wrap up. Cadmium has 8 naturally occurring isotopes. What do they have in common? Your options are atomic mass, mass number, number of protons, or number of neutrons. The correct answer here is C, number of protons. Every atom of cadmium has 48 protons in its nucleus, no matter how many neutrons it has. The next question reads, an atom of lithium loses an electron. What is the effect of this event? Your choices are, the atom of a different element has been formed. The atom becomes negatively charged. The atom becomes positively charged, or the atom acquires no charge. Here, the correct answer is C again. It becomes positively charged. Losing an electron doesn't change the number of protons, so the element is still lithium. But now there are more protons than electrons, giving the atom a net positive charge. So before we close, let's put together all of the most important ideas from today's lecture. First, every atom is made of 3 particles: protons, neutrons, and electrons. Protons and neutrons are found in the nucleus. Electrons move through the surrounding cloud. Second, the number of protons defines the element. 6 protons, always carbon. 8 protons, always oxygen. Change that number and you change the element itself. Third, isotopes are versions of the same element with different numbers of neutrons. They have the same identity but different mass and sometimes different stability. Fourth, the atomic mass on the periodic table is a weighted average of all of the naturally occurring isotopes. At this point, you should be able to generate a full and appropriate response to today's essential question. How does the structure of an atom determine both the identity of matter and the energy it can release?